This is Chapter 6. We'll be looking at Chapter 6.1 and 6.2 today, looking at simple trusses, and we will be looking at the method of joints is our method today of computing the forces in each member of a truss given some type of loading on a truss. We will also be doing the method of sections in the next module. But in both of these cases, we are going to be looking at whether the member is in tension or in compression, plus the magnitude of the force in that member. So looking at the truss that we have here, this is actually problem 6-16 in your book on page 289. So we'll be doing an example as well as discussing a few things. So if you would go and think about if I had a member and I pulled this member off the truss and I pulled on this member. So if you grabbed your pencil and pulled away on each end of your pencil, this would be in tension. And if I would push against each side of my pencil, careful with your lead, we are talking about compression. Oof, that was hard to spell. So back to my truss here. Each one of these is a member. We'll label them A, B. This would be B to C, C to D, D to E, and then we go back to E to A. And we also have B, E, and C, E. Here we have a roller at point E, and we have a pinned connection at point A. At each point here, these are called pins. So at point B we have a pin, at point C, point D, point E, point A. So they're all connected at pins. If I was to draw the free body diagram, I would redraw this whole thing, but I would have my reaction force shown, and I'm going to label that AY, and this one AX, and here I'm going to label this one EY. So those are my reaction forces on the actual truss itself due to the types of supports on here. In this problem here, we're asking to find the forces in each member. My approach is to solve for the reaction forces first, and then I'm going to use the method of joints, which includes the equilibrium equations. So let's go ahead and solve for my reaction forces. So my reaction forces. So if I sum my moment about point A is equal to 0, so now I'm just summing my moment right here. Now I don't have to worry about AX or AY again because they're going straight into the point. There's no perpendicular distance. But I have EY, and it is rotating in a counterclockwise around point A. So that's going to be positive, and that's going to be 4 meters away. Minus, now if I was to say that P, guess I have to give us a force there. Yeah, we'll call that 8 kilonewtons. 8 kilonewtons. So we know this is 8 meters away, and it is 8 kilonewtons. So 8 kilonewtons times 8 meters. It's all equal to 0. So I can say that EY is going to equal 16 kilonewtons. Now I can sum my forces in the Y, and I have AY plus 16 kilonewtons minus 8 kilonewtons is equal to 0. So here we get AY is equal to negative 8 kilonewtons. So what does that mean? Well, what that actually means is that this force is actually going down. To hold this pin is holding it down because of this force. It's rotating it clockwise, so it's actually holding this down. Okay, and then if I sum my forces in the X, we get 0. because there are no other forces in the x direction. So the method of joints, and the best way to discuss this is just by an example. So the method of joints, I'm going to look at each individual joint, and I can solve for the forces in each member by looking at these joints. So I could look at point A and solve for AB and AE. If I drew a free body diagram of E, that means I'm cutting all of those. I have 1, 2, 3, 4. That's going to be hard to solve for. I'm going to have 2 unknowns in the Y, 2 unknowns in the X, or 4 unknowns in the X. So that one's going to be a little bit more difficult. But if I go to point D, joint D, and I draw my free body diagram, I'm going to have the 8 kilonewton force that's acting down. I'm going to have joint CD, and I'm going to have joint CE. Now here's an important key, or an important point. I am drawing these in tension away from the joint. So I'm pulling away from the joint means they are in tension. If I compute this and it stays positive, that means that actual force is in tension. If it comes out negative, it is in compression. Okay, so here we know that this is 60 degrees. That was given to us. So if I sum my forces in the y direction, being positive, I am going to get that CD times the sine of 60 is minus 8 kilonewtons. So this is sine of 60, right? CD sine of 60 minus 8 kilonewtons is equal to 0. Now note, I know I said that if this was coming out, this is positive, this is in tension. But when I do my equilibrium equations, I forget about tension and compression, and I just look at the direction of the actual vectors. Okay, so here I would divide by sine of 60, take the 8 kilonewtons over, so CD comes out to be 9.23 kilonewtons. It comes out to be positive, so it is in tension. Now if I sum my forces in the x direction, going to the right is positive. I know that this is 9.23 now, and 9.23 is going left, so it is negative. So it's a negative 9.23 kilonewtons times cosine of 60 minus, remember ED is equal to 0. So plugging this into my calculator, I take this to the other side. This stays negative, so it's going to be a negative 4.62 kilonewtons. Now this would be in compression. Okay, so the next joint I'm going to look at is I'm going to come up to joint C. I know joint CD, so I know I can find CE and BC. So I will, again, draw my free body diagram. Joint C. Now, in this case, I'm drawing this again in tension. We know that CE is also we're going to have to solve for. And we know that CD was in tension, so we draw it in tension. And we know that it was 9.23 kilonewtons. We also know, if I drew, that this is 60 degrees and this is also 60 degrees. So if I sum my forces in the y, I'm going to kind of do this just to, if I sum my forces in the y, I get negative 9.23 times the sine of 60 minus CE times the sine of 60 is all equal to 0. So CE is 9.23 kilonewtons in compression. So that came out to be negative 9.23. If I sum my forces in the x now, I'm going to get negative BC plus 9.23 times the cosine of, cosine of 60. Cosine of 60 plus 9.23 times the cosine of 60 is all equal to 0. So we could say BC, after plugging that into my calculator, is 9.23 kilonewtons. That also came out negative, so which would be in compression. Kind of makes sense. Alright, so if we look at the next joint, let's look at joint B. Now when I look at joint B, it's going to look similar. It's going to be here, and here, and here. Now we said that BC is negative 9.23 kilonewtons. I'm going to take a step back really quick. When I look at my sum of my forces in the x here, this is negative BC. This is a positive 9.23 times cosine 60. Positive 9.23 times cosine 60 is equal to 0. So if I take the BC to the other side, this is actually positive. So this is actually in tension. Sorry about that. So if, and I'm hoping that you guys were screaming at the computer saying, no, no, that can't be. So for joint B, we said that this was 9.23 kilonewtons in tension. That was my correction. So this was 9.23 kilonewtons. And then I will be drawing BE in tension and BA also in tension. We also know that this is 60 degrees and this is 60 degrees. So by summing my forces in the y, I get that this is a negative sine of 60 times BA. So this is going down, sine of 60, because this is the force we're looking at right here, minus the sine of 60 times BE. And those are the only two forces that we would have in the y direction, would equal to 0. So by algebra, using my calculator, I get BE. Oh wait, let's take a look at that real quick. We can't solve for that right now, can we? Because we have BA and BE. So let's just take that off. No problem though. What I can do is I can sum my forces in the x, and I'm going to have the same two unknowns. So I'm going to have negative cosine of 60 times BA plus cosine of 60 times BE. Note that BA is going negative and BA is going, BA is going negative and BE is going positive, is equal to 0. So now I have two equations, two unknowns, and I forgot my negative, positive 9.23 here. Also plus 9.23. So by using two equations, two unknowns, put that into my calculator, I come up with 9.23 in tension, and BE is 9.23 in compression, and these are in kilonewtons. And then the last joint would be E. Let's scroll down just a little bit. So if I draw this free body diagram, we know that EY was 16 kilonewtons. We know that we are solving for AE. We know that member ED, this is ED, was what we're solving for. Nope, we have ED. We have ED from up here, 4.62, and it is going in compression. So we're pointing it into the joint. Again, CE over here. This nut should have been CE. This should have been ED. So ED was negative 4.62 kilonewtons, which would actually be going into the joint. So that's why I'm showing 4.62 kilonewtons going into the joint, because it is in compression. And then I had 9.23 kilonewtons for CE, which we solved for over here, and that is also in compression, so that's going into the joint. We solved for BE. BE was also 9.23 in compression, so that's also going in to the joint. And we are solving for AE. So by looking at this, I sum my forces in the X, because I'm solving for AE. I get 9.23 kilonewtons times the cosine of 60 minus 9.23 kilonewtons times the cosine of 60. That's these two here, this one here and this one here, minus 4.62 kilonewtons minus AE is equal to 0. Now why is AE going to the left? Because we're drawing it in tension. Everything else we've already solved for, and it was in compression, except for my reaction force here. We solved that it was going up into the support to help hold the truss into place. So by plugging this into my calculator, I get negative 4.62 kilonewtons in compression. Alright, so I will do one more example on the next video. Thanks.